Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the video on differentiating using the quotient rule, and in this video I'll just be going through a second example of the quotient rule. Okay, so we have to find dy dx given that y equals 6x minus 1 over 5x plus 2 all cubed, and we're going to do that using the quotient rule. How do we know it's the quotient rule? Because we're watching a video called the quotient rule, Mr. Southern. No, let's think about this. It's because we have a function of x divided by another function of x, and that's how we know to use the quotient rule. So that language of maths, quotient and dividing. Now, we always call the numerator u, and we always call the denominator v. So I'm going to identify straight away that u equals 6x minus 1, and that v equals 5x plus 2 cubed. And my first step is to differentiate each of those two functions in terms of x. So du dx is going to equal 6, and then let's just take our time on dv dx. We've got a function in a bracket, so function of a function. We're going to have to crack out the chain rule to differentiate this. So dv dx is going to be power down, so 3 5x plus 2 squared, one of the power that is, and multiply by the differential of the bracket, the differentiated bracket, which is just 5. So tidying that up, I have that dv dx is 15 lots of 5x plus 2 all squared. And I'm not going to expand that out at the moment, I'm just going to leave that as it is and substitute it into my formula for the quotient rule. So, my quotient rule. Get in the habit of writing this each time you use it. So v du dx minus u dv dx all over v squared, which is, right, let's look at this. V is 5x plus 2 cubed. So we have 5x plus 2 all cubed multiplied by du dx, which is 6. Multiplied by 6, then minus u, which is 6x minus 1. Important you have the bracket around that because it's a two-term expression. Multiplied by dv dx, which we've now got as 15 lots of 5x plus 2 all squared. And that is all over v squared. Now v is 5x plus 2 cubed. So 5x plus 2 cubed squared. I'll simplify that in just a moment. Now, what you can probably see here is I've got 5x plus 2, 5x plus 2, 5x plus 2. So I have the opportunity here to simplify this answer, which means that I'm not going to expand out those brackets at this time. Instead, what I'm going to do is I'm going to write 6 lots of 5x plus 2 cubed, so just putting the constant in front, so it's a more familiar form. And then I'm going to write minus 15 lots of 6x minus 1 times by 5x plus 2 all squared. That is all going to be over 5x plus 2 to the power of 6, because as you know, when you have powers either side of a bracket like this, you multiply. And now I need to look, okay, I've got 5x plus 2 cubed, I've got 5x plus 2 squared, and I've got 5x plus 2 to the power of 6. Now, what is the maximum amount of 5x plus 2? How many of those 5x plus 2s can I cancel here? Well, it's whichever term has the fewest of them. So 5x plus 2 squared can be cancelled entirely to 1. And that means that the power of 2 can be subtracted from each of the other 2 occasions that we see it. So that 3 can become a 1, and that 6 can become a 4, cancelling the term 5x plus 2 all squared to get a simpler final expression for dy dx. Now I'm going to do my expanding. So 6 times 5x, which is 30x. 6 times 2, so plus 12. Now this 5x plus 2 all squared has just gone to 1, so all I have here is minus 15 and then 6x minus 1 inside the bracket. So I can write that as minus 90x plus 15, and that's all over 5x plus 2 to the power of 4. And just as in the previous example, I'm not going to expand out this denominator, I'm going to leave it in factorised form. So all that's required to do now is just to finally simplify the numerator. I've got 30x, take 90x, that's negative 60x, and the 12 plus 15 is 27. So I'm actually going to write that as 27 minus 60x, just because it's neater, and that is all over 5x plus 2 to the power of 4. And that is my simplest form for dy dx for this function here. 27 minus 60x all over 5x plus 2 to the power of 4. One thing just worth noting is the way that I set out the bit in blue, where you have u, du dx, v and dv dx. You sometimes see students writing it as u and then du dx to the right of it, v, dv dx to the right of it. Don't do that. Do it in columns because it makes sense to differentiate downwards and integrate upwards. And what you'll meet when you come to do integration is something called integration by parts, and it's very, very useful to have it set out like this and be used to it, because you aren't given those two things, you're given those two things. But more on that when we get to it. Thanks for your company on the quotient rule. I'll see you again.